All right. So we talked about hash tables. Now the last thing that we're gonna talk about very briefly is trees. So trees are a decently big topic. We'll go a little more into it tomorrow and see how they relate to like recursion, stuff like that. But trees are, a tree is a data structure that has a root node, and each node can have children nodes, and then those children nodes can have children nodes. That is generally how a tree works. So there's a root, and then you can have multiple children. So this is just general trees. The one that you will most likely come across is called a binary tree. So a binary tree is a tree that can only have two children, a left, typically called left and right. So this is our root. You have a left and a right. So this, I guess the line is just a line connecting to the left and right. But yeah, so each piece of data is a node, and then each node contains a value. It contains a right pointer and a left pointer or reference. And then each one of these can have between 0 and 2. So it can have one child if we wanted. It can have none, and at most it can have 2. So that's a binary tree. A binary search tree So a binary search tree is a specific type of binary tree where everything to the left of a node is smaller. So left of node value is smaller. And then right of node val is larger. So a binary search tree is an ordered tree. So all the values are going to be in some form of order. That way, when you're searching it, it has a much faster search. So if you are similar, like we were saying, if we had a list and this list was in order, and we can look at the middle part and see, is the value that we're looking for greater than or less than the value that exists over here. If it's less than, then we only look through this part. If it's greater than, we only look through this part. Similarly, a binary search tree, you are only going to traverse the part of the tree that is relevant to you. So if you start at the root and you're looking for like a 7, let's say this is 10, this is 5, here's the 7, here's the 3, and this is like 12 and 14. So this is a valid binary search tree. If you're looking for 7, it's going to start at 10. It's going to see, should I go left or right? Left is smaller, right is bigger. It should go left. It's going to look at this one. Okay, I'm comparing 5 and 7. Should I go left or right? I should go right because 7 is larger than 5, and so on. So this is how a binary search tree is structured. So everything left has to be smaller, everything right has to be bigger. You might hear of something called a B tree. A B tree is not a binary search tree, just so you don't get confused if you see it. It's similar, but it can have more than 2 children per node. So it's not the same. Let's see some visualizations real quick. Let's see.
It's the first indexing. Yeah.
Thank you. Okay. So let's say we're going to insert, let's see if we can insert strings. No, we can only insert numbers. So let's start at 9. So this is the root. The value is 9. If we want to insert 3, goes to the left. Want to insert, give me a number.
1,000.
1,000. Let's do it. 1,000 goes to the left. If we insert 4, goes left and then right. We want to do 6, goes left, right, right. And so on. So it just keeps doing that. If we want to find something, I'm gonna slow down the animation a little bit. Let's say we want to find 6, or let's say we want to find 5, so something that doesn't exist. So it loops through 5, found 6, 6 was larger, it didn't have any children, so it said that it didn't find it. So it stopped here. Let's say we were looking for 2. Goes here, it doesn't find anything smaller than 3, so that means immediately you didn't find what you were looking for. Questions?
What happens if you try to add 14 again? Oh, got it. Thanks.
Yeah. So this one, I guess there is no, yeah, you can have duplicates. There might be special types of trees that you don't allow duplicates. Or if you're implementing it yourself in your code and you don't want to allow duplicates, then you shouldn't allow them. Yeah, so that's a pretty common tree that you will see quite a bit. Another type of tree that we're not really going to look into as much, but I want you guys to be aware of, in case you hear it, AVL trees. So AVL trees are a balanced binary search tree. So if you remember here, if we added like 7, 4, 8, let's add 3, let's add 2 or 1. Okay, so in an AVL tree, in a balanced tree, this would not be allowed. So an AVL tree requires you to have a height. So each subtree, so each child can only have a height difference of 1. So basically, this is height 1, this is height 3. So there's an imbalance here and it wouldn't be allowed. So let's see when we're trying to insert into an AVL tree what happens. So if we do a 9, let's insert a 5 to the left. Okay, let's insert, so these little numbers are the heights. Let's do a 9 again. Let's do 12. That's on the right side. So there's a difference of 1 between these two. So this one has 2 and this one has 1. That's still allowed. So if I try to insert something on this side that's larger, let's do 14. It is going to loop through, it's going to find out that the height was larger. So then it does like a rotation to rebalance the tree. So if I do, what did I insert again? 14. So if I slowed it down, it looks through, inserts it, and then as it's going back up, it's calculating the numbers. And if it finds a misbalance between the children, because this one over here was 3 and this one was 1, it then does a rotation. And there's a couple different types of rotations. But yeah, just so you're aware that this exists.
Can you add 15 to that?
What is it?
Can you add 15 to that?
15, yeah. Right?
Whoa.
Yes.
I
Yeah.
just had a quick general question. I'm just trying to think about, like, off the top of your head, do you know what kind of data will be best structured in this way, like in tree fashion?
In trees, data that needs to be searched. And can be. Here, let's look up common applications for trees. Or let's look up like binary search tree, maybe.
Sure, yeah.
Um. So used a lot in applications due to its ordered structure. BSTs are used for indexing and multi-level indexing, helpful for searching algorithms. So tomorrow, Benjamin will talk a little bit about some search algorithms, and those search algorithms use trees. So if you have use cases where you have to search through a lot of data fast, that's what a binary search tree would be used for. The lookup or the search times are much faster than iterating through stuff. Yeah.
Oh, so like, for example, if you're searching like Facebook for someone's name, that
Mhm.
would use a binary search tree based on like what letters are put in, because
Yeah,
it's super
actually,
fast. Okay.
yeah, I've seen like what is it called? A character tree? No. Yeah, Bing still it's not good. Let me see. Yeah, there was this one exercise, I think it was on LeetCode or something like that. It's a pretty common one, but basically traversing a word and trying to, like, you build a tree out of a word so you can find all the letters that are like, or all the words that are connected to it. This is a bad example. I'll try to find it and show it to you. But yeah.
Okay. Okay.
It
Thank
can
you.
be, it can be for that, like for autocomplete and finding like words that are related to other words and stuff like that. Other questions? Okay. One last algorithm that is, sorry, not algorithm. One last data structure that you might hear of is a graph. I know Geeks for Geeks has a pretty good graphs. Basically, a graph is pretty similar to a tree. It just has, instead of having like a head and sorry, like a root node and then everything else is children nodes, everything is either a node or a vertice. So if nodes are connected, let me see if they have it down here. I linked to this in the lesson today as well, if you're interested in reading about it. But basically you can represent a graph like this as either a matrix or a list, and the list is just, I'm not going to talk about the matrix, but I'm going to show you the list real quick. So this is an adjacency list. So you have all your nodes numbered out, and everything that is attached to it, that means that there's a connection between this node and that node. So what this line means is there's a connection between node 0 and 1, also between node 0 and 4. And if we go back up to the graph, 0 and 4 and 0 and 1. So that's what a graph is. This is typically used with finding shortest path to a destination. So something that you might an algorithm that you might hear of is Dijkstra's algorithm, which basically solves like finding the shortest path from one node to another, which is used a lot in maps and finding destinations. So if you have one location and there's all these cities that are attached to it, what is the fastest way to get from one city to another? And typically those cities are a network of graphs, a network of nodes that are connected to each other using vertices. And when you run the algorithm, you're finding what is the best way to get there. So graphs are also pretty important. We won't really learn how to implement them, but later on, if you're wanting to learn more about data structures, I think graphs are a pretty good place to go. Yeah, I think that's all for today. Any questions? Okay, so today's assignment, let me switch the sharing real quick. So
Zainab, somebody mentioned earlier in chat too that the README or the markdown file for today's lecture, it's linking to Sierra's assignments, not Tango's.
oh,
So everybody's getting 404s.
thank you for letting me know. Let me edit that real quick. Thank you. Yeah, if you just change this to Tango, it should work. I didn't see that issue because I have access to both of them. So thank you for catching it. Okay, now the links should work. But yeah, our assignment for today is implementing the data structures that we talked about. So you're going to be implementing a stack, a queue, a linked list. For these ones, there's some videos like explaining how each of them work and how they're implemented. There's some hints here. And then if you're done, stretch goal is constructing a binary tree and a binary search tree and a hash table. So we have quite a bit, we have enough to fill up the day today. If you are done and you want more data structure practice, let us know. We'll give you some more stuff to practice. If you want to work on some more OOP stuff, this is another exercise that we have. All right. Any questions? Okay, let me stop the recording.